Here is a short supplement to the lecture on CO insertion reactions. We discussed several classic reactions like the Monsanto's acetic acid process. We have discussed the Cativa process and other such carbon monoxide insertion, including hydroformylation reactions. But there are many variations of the CO insertion reactions in catalytic processes and also in stoichiometric reactions. So it turns out to be an extremely valuable and also an important reaction to study. So let me just give you a few more examples. And before I do that, I would like to emphasize the fact that there are two classic ways by which CO insertion can be useful in a catalytic reaction or a stoichiometric reaction. One case involves the migration of an alkyl group to a carbon monoxide, and then an acyl group is formed, or an aryl group inserts into carbon monoxide. Both are equally the same. The effect is to produce an acyl group. And subsequently, you could have a reductive elimination. The second step, or the second classic way by which you can have a useful carbon monoxide insertion reaction, is the situation when two neutral moieties are there. It could be an alkyne or an alkene and a carbon monoxide. Now you need to have an oxidative coupling before the reductive elimination can take place. So these two cases are distinctly different. These two cases are distinctly different. One of them involves a migratory insertion reaction followed by a reductive elimination. Whereas the case where you have only neutral species, alkynes, alkenes, and carbon monoxide interacting with the metal, you could have a carbon monoxide insertion as a result of oxidative coupling. We will illustrate this in the following slides. But these are two major pathways you need to keep in mind. Let me take the Pauson-Kahn reaction as a classic case. Here I have for you alkyne, an alkyne, and an alkene, and carbon monoxide. And in the product, you notice that there is an alkene or a double bond that is generated, and that is coming because of the way in which we have labeled them. You know clearly that this part is in fact the part that is having the double bond in the product is in fact coming from the alkyne. So the alkyne is responsible for the C double bond C part of the product. The carbon monoxide, of course, is clearly recognizable, and the alkene becomes the saturated moiety in the final product. So initially you have R C double bond C, and then you end up with a saturated C single bond C. And of course, you have made three new bonds, and these new bonds are clearly marked by the formation of a bond to a carbon monoxide. So it is the violet bonds that I'm drawing here, and a bond between the alkyne and the alkene. So these are the new bonds that are being formed. The reaction itself is catalyzed by CO2CO8, and that introduces another variation that one can have. Is the catalyst in its resting state a dinuclear intermediate? The active form is a dinuclear intermediate or a mononuclear intermediate. These are two distinct possibilities, and we can look at both possibilities. But I prefer the dinuclear intermediate for reasons that I will explain. First, since we have already clearly defined the way in which the reaction works, you can recognize the three groups of molecules which are being stitched together. You just have to coordinate the two fragments, the three fragments, the carbon monoxide, which is already attached to the cobalt, and the two free fragments, the two substrates that are coming in, the alkyne and the alkene. Let's coordinate them to the two cobalt moieties and then carry out an oxidative coupling reaction. So this turns out to be a fairly straightforward reaction because you form three new bonds right away, two between the carbon and the cobalt and one between the alkene and the alkyne. And because you're forming two new sigma bonds, you will have oxidation of the cobalt to cobalt 1. Each cobalt becomes cobalt 1. Notice that if I had done it on a single cobalt center, I would have to oxidize it to cobalt 2. That is the reason why I prefer a dinuclear intermediate undergoing oxidative coupling reaction. And you will also notice that in the final product that is formed is less sterically congested if I have a dinuclear intermediate. Subsequent to this oxidative coupling reaction, one can have a carbon monoxide insertion reaction. Now you might think, is this just a necessity because the product has a carbon monoxide? I do not think so, because if I were to do a reductive coupling after the oxidative coupling, the first step, if this intermediate underwent a reductive coupling reaction, then the product would have been a four-membered ring, and that would be a more strained ring. So the insertion of carbon monoxide from the intermediate that is written to form the intermediate that would look like this with a carbon monoxide, the alkyne part and the alkene part seems to be probably even a reversible step, but one which will give me a stable product with a five-membered ring. So the stable five-membered ring product is formed once a carbon monoxide insertion has taken place. And this is the Pauson-Kahn product. So you can see that how by using the dinuclear intermediate, you can just oxidize the cobalt to +1, carry out an oxidative coupling reaction, an insertion reaction, and then a reductive elimination step. A reductive elimination step happens in this step, in the last step, which leads to the product. So I could have done the previous reaction on a single cobalt intermediate, but that would have led to oxidation of cobalt 1 to cobalt 0 to cobalt 2. Now let me come to another reaction which is called the Dötz reaction. The Dötz reaction, actually there is an umlaut on top of the O, and that's why I'm calling it Dötz reaction and not a Dötz reaction. So the Dötz reaction is in fact a reaction between a carbene. So this is a carbene molecule, carbene complex to chromium, attached, reacting with an alkyne, and the carbene is a Fischer carbene, and so the Fischer carbene has got an aromatic ring system attached to it. For purposes of clarity, I'm going to replace the ring with only the single double bond attached to the carbene carbon. You'll soon see why. What you end up with is a system where you have the arene moiety attached to the alkyne with one carbon monoxide, one carbene, and the alkyne. So you have a new six-membered ring formation, but that six-membered ring formation involves the insertion of a carbon monoxide moiety, and that carbon monoxide moiety turns out to be an OH in the final product. It is present in the enol form. You also have an alkyne moiety, and the alkyne, let me mark it with a different color so that you can clearly recognize it. This is the alkyne moiety. So we have an alkyne moiety right here. So the carbon monoxide is here, the alkyne moiety is there, and the carbene moiety is in fact again marked in violet, but you can see that this is part of the ring system that I have drawn for you in this slide. So at the outset, it looks like a fairly complex reaction, and in fact, it is a complex reaction compared to the simple Monsanto's acetic acid process. This reaction is a lot more involved and complicated, and one can work out the reaction in a retrosynthetic way. It is not so easy, but one can do that in this case. So let me proceed. So here is a carbene, and I have drawn the arene moiety as a ring system. You'll notice that a carbene is a single carbon attached to the metal, and you have a C triple bond C as a two reactants. Now, let us simply react the alkyne and the carbene in the way in which a metathesis reaction would take place. So that means the alkyne is positioned in such a way that the C triple bond C and the C double bond Cr are parallel to each other. Now I can form a pericyclic type of reaction in which you have formation of two new bonds. Let me mark the two new bonds for you with the dotted lines, which I have done here. And in the product also, let me mark it with a red color so you can recognize it very easily. So these are the two new bonds that have been formed. The triple bond has become a double bond, and the double bond has become a single bond. And two new bonds, carbon-carbon bond and the chromium-carbon bond, have been formed. Notice that this is now a cyclobutene, metallocyclobutene intermediate, very similar to the intermediate that we would have had in the case of the metathesis reaction. You have a four-membered ring and carbon monoxides present on the chromium. So you can imagine a ring expansion reaction in which carbon monoxide is inserted. So this carbon monoxide has been inserted in the strained four-membered ring, a fairly straightforward migratory insertion of this vinylic carbon attached to chromium to an adjacent carbon monoxide group. That now forms a metallocyclopentene, which I will label as A. So metallocyclopentene has been formed, and this is labeled as A in this slide. And this intermediate A is something that can undergo reductive elimination, in which case you will end up with what you can see as a four-membered ring with an ene and a one. That would be extremely strained. So what happens is there are two possibilities. In fact, I thought of another possibility where you can have a second alkyl group migrating to a carbon monoxide and extending the ring further. But surprisingly, the chromium carbon bond, which is marked in a dark blue color, that migrates to the third position of this allylic moiety. Remember, this carbon atoms 2 and 3 are in fact part of a ring system. The carbon atoms 2 and 3 are part of a ring system, but it's not marked here. It is kind of hidden. But if you were to migrate this chromium carbon C1 bond, if you migrate it from this position to the third position, so in other words, if it were to migrate to the third position right here, then I would end up with the product which is shown here. Now, there are two steps that I have omitted. That is a reductive elimination and a 1,3 migration. So 1,3 migration plus a reductive elimination results in this product. Okay. So if I do a reductive elimination of the intermediate that would be formed, then I get a ketene as an intermediate, which can do a 2 plus 2 plus 2 cyclization, 2 plus 2 plus 2 cyclization. So that will be a thermally allowed 4n plus 2 rings cyclization that you can think of, which leads to this product which is shown here. So notice how you end up with a enone system, which is actually a phenol in a hidden form. And you can imagine how this enone can just tautomerize to form the product which is shown here. So this is slightly more complicated than the reactions that we have considered so far. The initial step is straightforward. Carbon monoxide step is also straightforward. But before the reductive elimination step, you have a ring expansion. And the ring expansion is motivated by the fact that if I were to do a reductive elimination right here of the intermediate A without doing the ring expansion, then I would end up with a strained ring system. Reductive elimination here would lead to a strained ring system. This would lead to a 4-membered ring, 4-carbon ring system, and which would be unstable. So it does a ring expansion reaction, and that ring expansion reaction finally allows you to make this larger ring system, which is shown here. So let me proceed from the Dötz reaction to another reaction, which is in fact a case where you can have 2 plus 2 plus 2 cycloaddition reaction of 3 alkynes. That will give you this product. That is one possibility. There is some amount of selectivity for the unsubstituted alkyne to coordinate, and that is why you get selectively this compound that is formed there. I put up this slide primarily to tell you that the intermediate that is formed is in fact a complex which has got an interesting structure. This is a reaction which is catalyzed by CO2CO8, and you'll notice that there is an oxidative coupling which is happening, but the oxidative coupling now has a possibility of forming a complex in which 2 allyl systems are interacting with the cobalt, and it spans the cobalt-cobalt bond. It kind of wraps around it, and so it is called a flyover complex. Reductive elimination of this flyover complex will give you the arene ring.